The following is a conversation with Chris Lattner. Currently, he's a senior director at Google, working on several projects including CPU, GPU, TPU accelerators for TensorFlow, Swift for TensorFlow, and all kinds of machine learning compiler magic going on behind the scenes. He's one of the top experts in the world on compiler technologies, which means he deeply understands the intricacies of how hardware and software come together to create efficient code. He created the LLVM compiler infrastructure project and the Clang compiler. He led major engineering efforts at Apple, including the creation of the Swift programming language. He also briefly spent time at Tesla as vice president of Autopilot software during the transition from Autopilot Hardware 1 to Hardware 2, when Tesla essentially started from scratch to build an in-house software infrastructure for Autopilot. I could have easily talked to Chris for many more hours. Compiling code down across the levels of abstraction is one of the most fundamental and fascinating aspects of what computers do, and he is one of the world's experts in this process. It's rigorous science, and it's messy, beautiful art. This conversation is part of the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, iTunes, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D. And now, here's my conversation with Chris Lattner. What was the first program you've ever written?
My first program.
Back. And when was it?
I think I started as a kid and my parents got a basic programming book. And so when I started, it was typing out programs from a book and seeing how they worked and then typing them in wrong and trying to figure out why they were not working right, that kind of stuff.
So basic, what was the first language that you remember yourself maybe falling in love with, like really connecting with?
I don't know. I mean, I feel like I've learned a lot along the way, and each of them have a different special thing about them. So I started in basic and then went like GW basic, which was the thing back in the DOS days, and then upgraded to Q basic and eventually Quick basic, which are all slightly more fancy versions of Microsoft Basic. Made the jump to Pascal and started doing machine language programming and assembly in Pascal, which was really cool. Turbo Pascal was amazing for its day. Eventually got into C, C++, and then kind of did lots of other weird things. So
I feel like you took the dark path, which is the you could have gone Lisp.
Yeah,
you could have gone higher level, sort of functional, philosophical, hippie route.
Yeah.
Instead, you went into like the dark arts of the C.
It was straight into the machine. Right?
Straight to the machine.
So started with basic Pascal and then assembly, and then wrote a lot of assembly. And
why?
Eventually did Smalltalk and other things like that, but that was not the starting point.
But so what is this journey into C? Is that in high school? Is that in college?
That was in high school, yeah. So and then that was really about trying to be able to do more powerful things than what Pascal could do, and also to learn a different world. C was really confusing to me with pointers and the syntax and everything, and it took a while. But Pascal is much more principled in various ways. C is more. I mean, it has its historical roots, but it's not as easy to learn.
With pointers, there's this memory management thing that you have to become conscious of. Is that the first time you start to understand that there's resources that you're supposed to manage?
Yeah. Well, so you have that in Pascal as well, but in Pascal, they use like the caret instead of the star, and there's some small differences like that, but it's not about pointer arithmetic. And in C, you end up thinking about how things get laid out in memory a lot more. Mm-hmm. And so in Pascal, you have allocating and deallocating and owning the memory, but just the programs are simpler and you don't have to. Well, for example, Pascal has a string type. And so you can think about a string instead of an array of characters, which are consecutive in memory. And so it's a little bit of a higher level abstraction.
So let's get into it. Let's talk about LLVM, C-Lang, and compilers.
Sure.
So can you tell me first what LLVM and C-Lang are, and how is it that you find yourself the creator and lead developer of one of the most powerful compiler optimization systems in use today?
Sure. So I guess they're different things. So let's start with what is a compiler.
Is
that a good place to start?
What are the phases of a compiler? What are the parts? Yeah. What is it? Okay.
So what is even a compiler used for? So the way I look at this is you have a two-sided problem of you have humans that need to write code, and then you have machines that need to run the program that the human wrote. And for lots of reasons, the humans don't want to be writing in binary and want to think about every piece of hardware. And so at the same time that you have lots of humans, you also have lots of kinds of hardware. And so compilers are the art of allowing humans to think at a level of abstraction that they want to think about, and then get that program, get the thing that they wrote to run on a specific piece of hardware. And the interesting and exciting part of all this is that there's now lots of different kinds of hardware, chips like x86 and PowerPC and ARM and things like that, but also high performance accelerators for machine learning and other things like that are also just different kinds of hardware, GPUs. These are new kinds of hardware. And at the same time, on the programming side of it, you have BASIC, you have C, you have JavaScript, you have Python, you have Swift, you have like lots of other languages that are all trying to talk to the human in a different way to make them more expressive and capable and powerful. And so compilers are the thing that goes from one to the other. Now,
end to end, from the very beginning to the very end.
End to end. And so you go from what the human wrote, and programming languages end up being about expressing intent, not just for the compiler and the hardware, but the programming language's job is really to capture an expression of what the programmer wanted that then can be maintained and adapted and evolved by other humans, as well as interpreted by the compiler. So when you look at this problem, you have, on the one hand, humans, which are complicated, and you have hardware, which is complicated. And so compilers typically work in multiple phases. And so the software engineering challenge that you have here is try to get maximum reuse out of the amount of code that you write, because these compilers are very complicated. And so the way it typically works out is that you have something called a front end or a parser that is language specific. And so you'll have a C parser, and that's what Clang is, or C++ or JavaScript or Python or whatever. That's the front end. Then you'll have a middle part, which is often the optimizer. And then you'll have a late part, which is hardware specific. And so compilers there's many different layers often, but these three big groups are very common in compilers. And what LLVM is trying to do is trying to standardize that middle and last part. And so one of the cool things about LLVM is that there are a lot of different languages that compile through to it. And so things like Swift, but also Julia, Rust, Clang for C, C++, Objective-C, like these are all very different languages, and they can all use the same optimization infrastructure, which gets better performance, and the same code generation infrastructure for hardware support. And so LLVM is really that layer that is common that all these different specific compilers can use.
And is it a standard, like a specification, or is it literally an implementation?
It's an implementation. And so it's, I think there's a couple of different ways of looking at it, right? Because it depends on which angle you're looking at it from. LLVM ends up being a bunch of code. Okay, so it's a bunch of code that people reuse and they build compilers with. We call it a compiler infrastructure because it's kind of the underlying platform that you build a concrete compiler on top of. But it's also a community. And the LLVM community is hundreds of people that all collaborate. And one of the most fascinating things about LLVM over the course of time is that we've managed somehow to successfully get harsh competitors in the commercial space to collaborate on shared infrastructure. And so you have Google and Apple, you have AMD and Intel, you have NVIDIA and AMD on the graphics side, you have Cray and everybody else doing these things. And like all these companies are collaborating together to make that shared infrastructure really, really great. And they do this not out of the goodness of their heart, but they do it because it's in their commercial interest of having really great infrastructure that they can build on top of, and facing the reality that it's so expensive that no one company, even the big companies, no one company really wants to implement it all themselves.
Expensive or difficult?
Both. That's a great point, because it's also about the skill sets.
Right.
And these, the skill sets are very hard to find.
How big is the LLVM? It always seems like with open source projects, the kind, and LLVM is open source?
Yes, it's open source. It's 19 years old now, so it's fairly old.
It seems like the magic often happens within a very small circle of people.
Yes.
At least their early birth and whatever.
Yes. So the LLVM came from a university project. And so I was at the University of Illinois. And there it was myself, my advisor, and then a team of 2 or 3 research students in the research group. And we built many of the core pieces initially. I then graduated and went to Apple. And at Apple, brought it to the products, first in the OpenGL graphics stack, but eventually to the C compiler realm, and eventually built Clang, and eventually built Swift and these things. Along the way, building a team of people that are really amazing compiler engineers that help build a lot of that. And so as it was gaining momentum and as Apple was using it, being open source and public and encouraging contribution, many others, for example, at Google, came in and started contributing. And in some cases, Google effectively owns Clang now because it cares so much about C++ and the evolution of that ecosystem. And so it's investing a lot in the C++ world and the tooling and things like that. And so likewise, NVIDIA cares a lot about CUDA. And so CUDA uses Clang and uses LLVM for graphics and GPU.
And so when you first started as a master's project, I guess, did you think it was going to go as far as it went? Were you crazy ambitious about it?
No.
I mean, it seems like a really difficult undertaking, a brave one.
Yeah, no, it was nothing like that. So, I mean, my goal when I went to the University of Illinois was to get in and out with a non-thesis master's in a year and get back to work. So I was not planning to stay for 5 years and build this massive infrastructure. I got nerd sniped into staying. Yeah. And a lot of it was because LLVM was fun and I was building cool stuff and learning really interesting things and facing both software engineering challenges, but also learning how to work in a team and things like that. I had worked at many companies as interns before that, but it was really a different thing to have a team of people that are working together and trying to collaborate in version control, and it was just a little bit different.
Like I said, I just talked to Don Knuth, and he believes that 2% of the world population have something weird with their brain, that they're geeks. They understand computers. They're connected with computers. He put it at exactly 2%. Okay, so
he's a specific guy.
It's very, very specific. Well, he says I can't prove it, but it's very empirically there. Is there something that attracts you to the idea of optimizing code? I mean, it seems like that's one of the biggest, coolest things about LLVM.
Yeah, that's one of the major things it does. So I got into that because of a person, actually. So when I was in my undergraduate, I had an advisor or a professor named Steve Vegdahl. And I went to this little tiny private school. There were, I think, 7 or 9 people in my computer science department, or students in my class. So it was a very tiny, very, very small school. It was kind of a wart on the side of the math department kind of a thing at the time. I think it's evolved a lot in the many years since then. But Steve Vegdahl was a compiler guy, and he was super passionate. And his passion rubbed off on me. And one of the things I like about compilers is that they're large, complicated software pieces. And so one of the culminating classes that many computer science departments, at least at the time, did was to say that you would take algorithms and data structures and all these core classes, but then the compilers class was one of the last classes you take because it pulls everything together, and then you work on one piece of code over the entire semester. And so you keep building on your own work, which is really interesting. And it's also very challenging because in many classes, if you don't get a project done, you just forget about it and move on to the next one and get your B or whatever it is. But here you have to live with the decisions you make and continue to reinvest in it. And I really like that. And so I did a extra study project with him the following semester, and he was just really great. And he was also a great mentor in a lot of ways. And so from him and from his advice, he encouraged me to go to graduate school. I wasn't super excited about going to grad school. I wanted the master's degree, but I didn't want to be an academic. And but like I said, I kind of got tricked into staying and was having a lot of fun, and I definitely do not regret it.
What aspects of compilers were the things you connected with? So LLVM, there's also the other part that's just really interesting if you're interested in languages, is parsing and just analyzing like yeah, analyzing the language,
Yeah.
breaking it down, parsing, and so on. Was that interesting to you, or were you more interested in optimization?
For me, it was more. So I'm not really a math person. I can do math. I understand some bits of it when I get into it, but math is never the thing that attracted me. And so a lot of the parser part of the compiler has a lot of good formal theories that Don, for example, knows quite well. Still waiting for his book on that, but but I just like building a thing and seeing what it could do and exploring and getting to do more things and then setting new goals and reaching for them and with in the case of LLVM, when I started working on that, my research advisor that I was working for was a compiler guy, and so he and I specifically found each other because we were both interested in compilers, and so I started working with him and taking his class. And a lot of LLVM initially was, it's fun implementing all the standard algorithms and all the things that people had been talking about and were well known, and they were in the curricula for advanced studies in compilers. And so just being able to build that was really fun, and I was learning a lot by, instead of reading about it, just building. And so I enjoyed that.
So you said compilers are these complicated systems. Can you even just with language try to describe, how you turn a C++ program
Yes.
into code? Like, what are the hard parts? Why is it so hard?
So I'll give you examples of the hard parts along the way. So C++ is a very complicated programming language. It's something like 1,400 pages in the spec. So C++ by itself is crazy complicated.
Can we just, pause. What makes the language complicated in terms of what's syntactically like?
So it's what they call syntax. So the actual how the characters are arranged. Yes. It's also semantics, how it behaves. It's also, in the case of C++, there's a huge amount of history. C++ built on top of C. You play that forward, and then a bunch of suboptimal, in some cases, decisions were made, and they compound. And then more and more and more things keep getting added to C++, and it will probably never stop. But the language is very complicated from that perspective. And so the interactions between subsystems is very complicated. There's just a lot there. And when you talk about the front end, one of the major challenges, which Clang as a project, the C compiler that I built, I and many people built, one of the challenges we took on was we looked at GCC. Okay, GCC at the time was like a really good industry standardized compiler that had really consolidated a lot of the other compilers in the world and was a standard, but it wasn't really great for research. The design was very difficult to work with, and it was full of global variables and other things that made it very difficult to reuse in ways that it wasn't originally designed for. And so with Clang, one of the things that we wanted to do is push forward on better user interface. So make error messages that are just better than GCCs. And that's actually hard because you have to do a lot of bookkeeping in an efficient way to be able to do that. We want to make compile time better. And so compile time is about making it efficient, which is also really hard when you're keeping track of extra information. We wanted to make new tools available. So refactoring tools and other analysis tools that the GCC never supported, also leveraging the extra information we kept, but enabling those new classes of tools that then get built into IDEs. And so that's been one of the areas that Clang has really helped push the world forward in the tooling for C and C++ and things like that. But C++ and the front end piece is complicated, and you have to build syntax trees, and you have to check every rule in the spec, and you have to turn that back into an error message to the human that the human can understand when they do something wrong. But then you start doing the what's called lowering. So going from C++ and the way that it represents code down to the machine. And when you do that, there's many different phases you go through. Often there are, I think LLVM has something like 150 different what are called passes in the compiler that the code passes through. And these get organized in very complicated ways, which affect the generated code and the performance and compile time and many other things.
What are they passing through? So after you do the Clang parsing, what's the graph? What does it look like? What's the data structure here?
Yeah, so in the parser, it's usually a tree, and it's called an abstract syntax tree. And so the idea is you have a node for the plus that the human wrote in their code, or the function call, you'll have a node for call with the function that they call and the arguments they pass, things like that. This then gets lowered into what's called an intermediate representation. And intermediate representations are like LLVM has one. And there it's it's what's called a control flow graph. And so you represent each operation in the program as a very simple, like this is going to add two numbers, this is going to multiply two things, maybe we'll do a call, but then they get put in what are called blocks. And so you get blocks of these straight line operations, where instead of being nested like in a tree, it's straight line operations. And so there's a sequence and an ordering to these operations.
So
and then
within the block or outside the block?
That's within the block. And so it's a straight line sequence of operations within the block. And then you have branches, like conditional branches between blocks. And so when you write a loop, for example, in a syntax tree, you would have a for node, like for a for statement in a C-like language, you'd have a for node. Then you have a pointer to the expression for the initializer, a pointer to the expression for the increment, a pointer to the expression for the comparison, a pointer to the body. Okay, and these are all nested underneath it. In a control flow graph, you get a block for the code that runs before the loop, so the initializer code. Then you have a block for the body of the loop, and so the body of the loop code goes in there, but also the increment and other things like that. And then you have a branch that goes back to the top, and a comparison and a branch that goes out. And so it's more of a assembly level kind of representation. But the nice thing about this level of representation is it's much more language independent. And so there's lots of different kinds of languages with different kinds of, JavaScript has a lot of different ideas of what is false, for example, and all that can stay in the front end, but then that middle part can be shared across all of those.
How close is that intermediate representation to neural networks, for example? Are they because everything you describe is a kind of echoes of a neural network graph. Are they neighbors or what?
They're quite different in details, but they're very similar in idea. So one of the things that neural networks do is they learn representations for data at different levels of abstraction, right? And then they transform those through layers, right? So the compiler does very similar things, but one of the things the compiler does is it has relatively few different representations. Where a neural network often, as you get deeper, for example, you get many different representations, and each, layer or set of ops is transforming between these different representations. In a compiler, often you get one representation and they do many transformations to it. And these transformations are often applied iteratively, for programmers, there's familiar types of things. For example, trying to find expressions inside of a loop and pulling them out of a loop so that they execute fewer times, or find redundant computation, or find constant folding or other simplifications, turning 2 times x into x shift left by 1, and things like this are all the examples of the things that happen. But compilers end up getting a lot of theorem proving and other kinds of algorithms that try to find higher level properties of the program that then can be used by the optimizer.
Cool. So what's like the biggest bang for the buck with optimization? What's
today? Yeah.
Well, no, not even today. At the very beginning, the 80s, I don't know. But
okay, yeah. So for the 80s, a lot of it was things like register allocation. So the idea of in a modern, like a microprocessor, what you'll end up having is you'll end up having memory, which is relatively slow, and then you have registers that are relatively fast. But registers, you don't have very many of them. Okay. And so when you're writing a bunch of code, you're just saying like, compute this, put it in temporary variable, compute this, compute this, compute this, put it in temporary variable. I have a loop. I have some other stuff going on. Well, now you're running on an x86, like a desktop PC or something. Well, it only has, in some cases, some modes, 8 registers, right? And so now the compiler has to choose what values get put in what registers at what points in the program. And this is actually a really big deal. So if you think about, you have a loop, an inner loop that executes millions of times maybe. If you're doing loads and stores inside that loop, then it's going to be really slow. But if you can somehow fit all the values inside that loop in registers, now it's really fast. And so getting that right requires a lot of work because there's many different ways to do that. And often what the compiler ends up doing is it ends up thinking about things in a different representation than what the human wrote, right? You wrote int x. Well, the compiler thinks about that as 4 different values, each which have different lifetimes across the function that it's in. And each of those could be put in a register or memory or different memory, or maybe in some parts of the code recomputed instead of stored and reloaded. And there are many of these different kinds of techniques that can be used.
So it's adding almost like a time dimension to, it's trying to optimize across time. So it's considering when you're programming, you're not thinking in that way.
Absolutely. And so the RISC era, made things
Risk?
so RISC chips, RISC, the RISC chips as opposed to CISC chips. The RISC chips made things more complicated for the compiler because what they ended up doing is ending up adding pipelines to the processor where the processor can do more than one thing at a time. But this means that the order of operations matters a lot. And so one of the classical compiler techniques that you use is called scheduling. And so moving the instructions around so that the processor can keep its pipelines full instead of stalling and getting blocked. And so there's a lot of things like that that are kind of bread and butter compiler techniques that have been studied a lot over the course of decades now. But the engineering side of making them real is also still quite hard. And you talk about machine learning. This is a huge opportunity for machine learning because many of these algorithms are full of these like hokey hand-rolled heuristics, which work well on specific benchmarks but don't generalize, and full of magic numbers. And I hear there's some techniques that are good at handling that.
So, what would be the if you were to apply machine learning to this? What's the thing you're trying to optimize? Is it ultimately the running time?
You can pick your metric, and there's running time, there's memory use, there's lots of different things that you can optimize for. Code size is another one that some people care about in the embedded space.
Is this like the thinking into the future, or has somebody actually been crazy enough to try to have machine learning based parameter tuning for optimization of compilers?
So this is something that is, I would say, research right now. There are a lot of research systems that have been applying search in various forms, and using reinforcement learning is one form, but also brute force search has been tried for quite a while. And usually these are in small problem spaces. So find the optimal way to code generate a matrix multiply for a GPU, right? Something like that, where you say, there's a lot of design space of, do you unroll loops a lot? Do you execute multiple things in parallel? And there's many different confounding factors here because graphics cards have different numbers of threads and registers and execution ports and memory bandwidth and many different constraints that interact in nonlinear ways. And so search is very powerful for that. And it gets used in certain ways, but it's not very structured. This is something that we as an industry need to fix.
So you said 80s, but have there been like big jumps in improvement and optimization?
Yeah.
Since then, what's the coolest things
it's largely been driven by hardware. So, hardware and software. So in the mid 90s, Java totally changed the world, right? And I'm still amazed by how much change was introduced by Java.
In a good way, or
in a good way. So like reflecting back, Java introduced things like all at once introduced things like JIT compilation. None of these were novel, but it pulled it together and made it mainstream and made people invest in it. JIT compilation, garbage collection, portable code, safe code, like memory safe code, like a very dynamic dispatch execution model. Like many of these things, which had been done in research systems and had been done in small ways in various places, really came to the forefront and really changed how things worked, and therefore changed the way people thought about the problem. JavaScript was another major world change based on the way it works. But also on the hardware side of things, multi-core and vector instructions really change the problem space and are very, they don't remove any of the problems that compilers faced in the past, but they add new kinds of problems of how do you find enough work to keep a 4-wide vector busy, right? Or if you're doing a matrix multiplication, how do you do different columns out of that matrix at the same time, and how do you maximally utilize the arithmetic compute that one core has, and then how do you take it to multiple cores? And
how did the whole virtual machine thing change the compilation pipeline?
So what the Java virtual machine does is it splits, just like I was talking about before, where you have a front end that parses the code, and then you have an intermediate representation that gets transformed. What Java did was they said, we will parse the code and then compile to what's known as Java bytecode. Mm-hmm. And that bytecode is now a portable code representation that is industry standard and locked down and can't change. And then the back part of the compiler that does optimization and code generation can now be built by different vendors. Okay. And Java bytecode can be shipped around across the wire. It's memory safe and relatively trusted.
And because of that, it can run in the browser.
And that's why it runs in the browser.
Yeah.
Right. And so that way you can be in, again, back in the day, you would write a Java applet and you'd use as a web developer, you'd build this mini app that would run on a web page. Well, a user of that is running a web browser on their computer. You download that Java bytecode, which can be trusted, and then you do all the compiler stuff on your machine so that you know that you trust that.
Now, was that a good idea or a bad idea?
It's a great idea. I mean, it's a great idea for certain problems. And I'm very much a believer that technology is itself neither good nor bad. It's how you apply it. This would be a very, very bad thing for very low levels of the software stack. But in terms of solving some of these software portability and transparency or portability problems, I think it's been really good. Now, Java ultimately didn't win out on the desktop. And there are good reasons for that. But it's been very successful on servers and in many places. It's been a very successful thing over decades.
So what has been LLVM's and CLang's improvements in optimization that throughout its history? What are some moments where you had set back and really proud of what's been accomplished?
Yeah, I think that the interesting thing about LLVM is not the innovations in compiler research. It has very good implementations of various important algorithms, no doubt. And a lot of really smart people have worked on it. But I think that the thing that's most profound about LLVM is that through standardization, it made things possible that otherwise wouldn't have happened. Okay. And so interesting things that have happened with LLVM, for example, Sony has picked up LLVM and used it to do all the graphics compilation in their movie production pipeline. And so now they're able to have better special effects because of LLVM. That's kind of cool. That's not what it was designed for, right? But that's the sign of good infrastructure when it can be used in ways it was never designed for because it has good layering and software engineering and it's composable and things like that.
Which is where, as you said, it differs from GCC.
Yes. GCC is also great in various ways, but it's not as good as a infrastructure technology. It's really a C compiler or it's a Fortran compiler. It's not infrastructure in the same way.
Now, is it? Now you can tell I don't know what I'm talking about because I keep saying CLang. You could always tell when a person is clueless by the way I pronounce something. I don't think have I ever used Clang.
Entirely possible. So you've used code it's generated probably. So Clang and LLVM are used to compile all the apps on the iPhone effectively and the OSs. It compiles Google's production server applications. It's used to build like GameCube games and PlayStation 4 and things like that.
So as a user I have, but just everything I've done that I experienced with Linux has been, I believe, always GCC.
Yeah, I think Linux still defaults to GCC.
And is there a reason for that? Or is it, is there a reason for that?
It's a combination of technical and social reasons. Many Linux developers do use Clang, but the distributions for lots of reasons use GCC historically, and they've not switched. Yeah.
Because it's just anecdotally online, it seems that LLVM has either reached the level of GCC or superseded on different features or whatever. So,
the way I would say it is that they're so close it doesn't matter.
Yeah, exactly.
Like they're slightly better in some ways, slightly worse in other ways, but it doesn't actually really matter anymore at that level.
So in terms of optimization breakthroughs, it's just been solid incremental work.
Yeah. Which describes a lot of compilers. The hard thing about compilers, in my experience, is the engineering, the software engineering, making it so that you can have hundreds of people collaborating on really detailed, low-level work and scaling that. And that's really hard. And that's one of the things I think LLVM has done well. And that kind of goes back to the original design goals with it to be modular and things like that. And incidentally, I don't want to take all the credit for this, right? I mean, some of the best parts about LLVM is that it was designed to be modular. And when I started, I would write, for example, a register allocator, and then somebody much smarter than me would come in and pull it out and replace it with something else that they would come up with. And because it's modular, they were able to do that. And that's one of the challenges with GCC, for example, is replacing subsystems is incredibly difficult. It can be done, but it wasn't designed for that. And that's one of the reasons that LLVM has been very successful in the research world as well.
But in the community sense, Guido van Rossum, right, from Python, just retired from what is it? Benevolent dictator for life, right? So in managing this community of brilliant compiler folks, did it for a time at least fall on you to approve things?
Oh yeah. So I mean, I still have something like an order of magnitude more patches in LLVM than anybody else. And many of those I wrote myself. But
So you still write? I mean, you're still close to the I don't know what the expression is, to the metal. You still write code.
I still write code. Not as much as I was able to in grad school, but that's an important part of my identity. But the way that LLVM has worked over time is that when I was a grad student, I could do all the work and steer everything and review every patch and make sure everything was done exactly the way my opinionated sense felt like it should be done. And that was fine. But as things scale, you can't do that, right? And so what ends up happening is LLVM has a hierarchical system of what's called code owners. These code owners are given the responsibility not to do all the work, not necessarily to review all the patches, but to make sure that the patches do get reviewed and make sure that the right thing's happening architecturally in their area. And so what you'll see that, for example, hardware manufacturers end up owning the hardware specific parts of their hardware. That's very common. Leaders in the community that have done really good work naturally become the de facto owner of something. And then usually somebody else is like, how about we make them the official code owner? And then we'll have somebody to make sure that all the patches get reviewed in a timely manner. And then everybody's like, yes, that's obvious. And then it happens, right? And usually this is a very organic thing, which is great. And so I'm nominally the top of that stack still, but I don't spend a lot of time reviewing patches. What I do is I help negotiate a lot of the technical disagreements that end up happening and making sure that the community as a whole makes progress and is moving in the right direction and doing that. So we also started a nonprofit 7 years ago. Time's gone away. And the nonprofit, the LLVM Foundation nonprofit, helps oversee all the business sides of things and make sure that the events that the LLVM community has are funded and set up and run correctly and stuff like that. But the foundation is very much stays out of the technical side of where the project is going.
Right. So it sounds like a lot of it is just organic. Just
Yeah. Well, and LLVM is almost 20 years old, which is hard to believe. Yeah. Somebody pointed out to me recently that LLVM is now older than GCC was when LLVM started. Right. So time has a way of getting away from you, but the good thing about that is it has a really robust, really amazing community of people that are in their professional lives spread across lots of different companies, but it's a community of people that are interested in similar kinds of problems and have been working together effectively for years and have a lot of trust and respect for each other. And even if they don't always agree, that we're able to find a path forward.
So then in a slightly different flavor of effort, you started at Apple in 2005 with the task of making, I guess, LLVM production ready. Yep. And then eventually 2013 through 2017, leading the entire developer tools department. We're talking about LLVM, Xcode, Objective-C to Swift. So in a quick overview of your time there, what were the challenges? First of all, leading such a huge group of developers. What was the big motivator, dream, mission behind creating Swift, the early birth of it from Objective-C and so on, and Xcode? What are some challenges?
So these are different questions.
Yeah, I know. But
okay,
I want to talk about the other stuff too. So
I'll stay on the technical side, then we could talk about the big team pieces. If that's okay. Sure. So it's to really oversimplify many years of hard work. LLVM started, joined Apple, became a thing, became successful, and became deployed. But then there's a question about how do we actually parse the source code? So LLVM is that back part, the optimizer and the code generator. And LLVM is really good for Apple as it went through a couple of hardware transitions. I joined right at the time of the Intel transition, for example, and 64-bit transitions, and then the transition to ARM with the iPhone. And so LLVM was very useful for some of these kinds of things. But at the same time, there's a lot of questions around developer experience. And so if you're a programmer pounding out, at the time, Objective-C code, the error message you get, the compile time, the turnaround cycle, the tooling in the IDE were not great, or not as good as they could be. And so, as I occasionally do, I'm like, well, okay, how hard is it to write a C compiler?
Right.
And so I'm not going to commit to anybody. I'm not going to tell anybody. I'm just going to just do it on nights and weekends and start working on it. And then, I built up in C, there's this thing called the preprocessor, which people don't like, but it's actually really hard and complicated and includes a bunch of really weird things like trigraphs and other stuff like that are really nasty. And it's the crux of a bunch of the performance issues in the compiler. Started working on the parser and kind of got to the point where I'm like, oh, you know what? We could actually do this. Everybody's saying that this is impossible to do, but it's actually just hard. It's not impossible. And eventually told my manager about it, and he's like, oh, wow, this is great. We do need to solve this problem. Oh, this is great. We can get you one other person to work with you on this, And slowly a team is formed and it starts taking off. And C++, for example, a huge, complicated language. People always assume that it's impossible to implement, and it's very nearly impossible, but it's just really, really hard. And the way to get there is to build it one piece at a time, incrementally. And that was only possible because we were lucky to hire some really exceptional engineers that knew various parts of it very well and could do great things. Swift was kind of a similar thing. So Swift came from, we were just finishing off the first version of C++ support in Clang. And C++ is a very formidable and very important language, but it's also ugly in lots of ways. And you can't implement C++ without thinking there has to be a better thing, right? And so I started working on Swift, again, with no hope or ambition that would go anywhere. Just let's see what could be done. Let's play around with this thing. It was, me in my spare time, not telling anybody about it, kind of a thing. And it made some good progress. I'm like, actually, it would make sense to do this. At the same time, I started talking with the senior VP of software at the time, a guy named Bertrand Surlet. And Bertrand was very encouraging. He was like, well, let's have fun. Let's talk about this. And he was a little bit of a language guy. And so he helped guide some of the early work and encouraged me and got things off the ground. And eventually told my manager and told other people. And it started making progress. The complicating thing with Swift was that the idea of doing a new language is not obvious to anybody, including myself. And the tone at the time was that the iPhone was successful because of Objective-C. Right?
Oh, interesting.
And
not despite of, or just
correct.
Because of. Yeah.
And you have to understand that at the time, Apple was hiring software people that loved Objective-C. Right? And it wasn't that they came despite Objective-C. They loved Objective-C, and that's why they got hired. And so you had a software team that the leadership in many cases went all the way back to Next, where Objective-C really became real. And so they quote unquote grew up writing Objective-C, and many of the individual engineers all were hired because they loved Objective-C. And so this notion of, okay, let's do new language was kind of heretical in many ways, right? Meanwhile, my sense was that the outside community wasn't really in love with Objective-C. Some people were, and some of the most outspoken people were, but other people were hitting challenges because it has very sharp corners and it's difficult to learn. And so one of the challenges of making Swift happen that was totally non-technical is the social part of what do we do? Like if we do a new language, which at Apple, many things happen that don't ship, right? Mm-hmm. So if we ship it, what is the metrics of success? Why would we do this? Why wouldn't we make Objective-C better? If Objective-C has problems, let's file off those rough corners and edges. Mm-hmm. And one of the major things that became the reason to do this was this notion of safety, memory safety. And the way Objective-C works is that a lot of the object system and everything else is built on top of pointers in C. Mm-hmm. Objective-C is an extension on top of C. And so pointers are unsafe. And if you get rid of the pointers, it's not Objective-C anymore. All right. And so fundamentally, that was an issue that you could not fix safety or memory safety without fundamentally changing the language. And so once we got through that part of the mental process and the thought process, it became a design process of saying, okay, well, if we're going to do something new, what is good? Like, how do we think about this? And what do we like? And what are we looking for? And that was a very different phase of it.
So what are some design choices early on in Swift? Like we're talking about braces, Are you making a typed language or not?
Yeah.
All those kinds of things.
Yeah, so some of those were obvious given the context. So a typed language, for example, Objective-C is a typed language, and going with an untyped language wasn't really seriously considered. We wanted the performance, and we wanted refactoring tools and other things like that that go with typed languages.
Quick dumb question.
Yeah.
Was it obvious? I think this will be a dumb question, but was it obvious that the language has to be a compiled language, not an?
Yes, that's not a dumb question. Earlier, I think late 90s, Apple had seriously considered moving its development experience to Java. But Swift started in 2010, which was several years after the iPhone, and it was when the iPhone was definitely on an upward trajectory, and the iPhone was still extremely, and is still a bit memory constrained, right? And so being able to compile the code and then ship it, and then having standalone code that is not JIT compiled is a very big deal, and it's very much part of the Apple value system. Okay. Now, JavaScript's also a thing, right? I mean, it's not that this is exclusive, and technologies are good depending on how they're applied, right? But in the design of Swift, saying like, how can we make Objective-C better, right? Objective-C is statically compiled, and that was the contiguous, natural thing to do.
Just skip ahead a little bit. Now we'll right back. Just as a question, as you think about today in 2019, in your work at Google, TensorFlow, and so on, is again compilation, static compilation,
still the right thing.
Still the right thing.
Yeah. So the funny thing after working on compilers for a really long time is that, and this is one of the things that LLVM has helped with, is that I don't look at compilations being static or dynamic or interpreted or not. This is a spectrum. Okay. And one of the cool things about Swift is that Swift is not just statically compiled. Mm-hmm. It's actually dynamically compiled as well. And it can also be interpreted, though nobody's actually done that. And so what ends up happening when you use Swift in a workbook, for example, in Colab or in Jupyter, is it's actually dynamically compiling the statements as you execute them. And so this gets back to the software engineering problems, mm-hmm. right? Where if you layer the stack properly, you can actually completely change how and when things get compiled because you have the right abstractions there. And so the way that a Colab workbook works with Swift is that when you start typing into it, it creates a process, a Unix process. And then each line of code you type in, it compiles it through the Swift compiler, the front end part, and then sends it through the optimizer. JIT compiles machine code, and then injects it into that process. And so as you're typing new stuff, it's like squirting in new code and overwriting and replacing and updating code in place. And the fact that it can do this is not an accident. Like Swift was designed for this, but it's an important part of how the language was set up and how it's layered. And this is a non-obvious piece. And one of the things with Swift that was, for me, a very strong design point is to make it so that you can learn it very quickly. And so from a language design perspective, the thing that I always come back to is this UI principle of progressive disclosure of complexity. And so in Swift, you can start by saying print, quote, hello world, quote, right? And there's no /n, just like Python, one line of code, no main, no
header files.
No header files, no public static class void, blah, 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 string like Java has, right? It's one line of code, right? And you can teach that and it works great. Then you can say, well, let's introduce variables. And so you can declare a variable with var. So var x equals 4. What is a variable? You can use x plus 1. This is what it means. Then you can say, well, how about control flow? Well, this is what an if statement is. This is what a for statement is. This is what a while statement is. And then you can say, let's introduce functions, right? And many languages like Python have had this kind of notion of let's introduce small things, and then you can add complexity. Then you can introduce classes, and then you can add generics in the case of Swift, and then you can in modules and build out in terms of the things that you're expressing. But this is not very typical for compiled languages. And so this was a very strong design point, and one of the reasons that Swift in general is designed with this factoring of complexity in mind, so that the language can express powerful things. You can write firmware in Swift if you want to, but it has a very high level feel, which is really this perfect blend, because often you have very advanced library writers that want to be able to use the nitty gritty details, but then other people just want to use the libraries and work at a higher abstraction level.
It's kind of cool that I saw that you can just interoperability. I don't think I pronounced that word enough, but you can just drag in Python. It's just straight. You can import, like, I saw this in the demo.
Yeah.
Import, not like, how do you make that happen?
Yeah. Well,
what's up with?
yeah.
Is that as easy as it looks, or is it?
Yeah, it's as easy as it looks. That's not a stage magic hack or anything like that.
No, I don't mean from the user perspective. I mean from the implementation perspective to make it happen.
So it's easy once all the pieces are in place. The way it works. So if you think about a dynamically typed language like Python, right? You can think about it as in two different ways. You can say it has no types, right? Which is what most people would say. Or you can say it has one type, right? And you can say it has one type and it's like the Python object, right? And the Python object gets passed around, and because there's only one type, it's implicit, okay? And so what happens with Swift and Python talking to each other, Swift has lots of types, right? It has arrays and it has strings and all like classes and that kind of stuff. But it now has a Python object type, right? So there is one Python object type. And so when you say import NumPy, what you get is a Python object, which is the NumPy module. And then you say np.array, and it says, okay, hey Python object, I have no idea what you are. Give me your array member. Right? Okay, cool. And it just uses dynamic stuff, talks to the Python interpreter and says, hey Python, what's the .array member in that Python object? It gives you back another Python object. And now you say parentheses for the call and the arguments you're going to pass. And so then it says, hey, a Python object that is the result of np.array, call with these arguments, right? And again, calling into the Python interpreter to do that work. And so right now, this is all really simple. And if you dive into the code, what you'll see is that the Python module in Swift is something like 1,200 lines of code or something. It's written in pure Swift. It's super simple, and it's built on top of the C interoperability because it just talks to the Python interpreter. But making that possible required us to add two major language features to Swift to be able to express these dynamic calls and the dynamic member lookups. And so what we've done over the last year is we've proposed, implement, standardized, and contributed new language features to the Swift language in order to make it so it is really trivial. Right? And this is one of the things about Swift that is critical to the Swift for TensorFlow work, which is that we can actually add new language features, and the bar for adding those is high, but it's what makes it possible.
So you're now at Google doing incredible work on several things, including TensorFlow. So TensorFlow 2.0 or whatever leading up to 2.0 has by default in 2.0 has eager execution. And yet in order to make code optimized for GPU or TPU or some of these systems, computation needs to be converted to a graph. So what's that process like? What are the challenges there?
Yeah, so I'm tangentially involved in this, but the way that it works with autograph is that you mark your function with a decorator, and when Python calls it, that decorator is invoked, and then it says, before I call this function, you can transform it. And so the way autograph works is, as far as I understand, is it actually uses the Python parser to go parse that, turn it into a syntax tree, and now apply compiler techniques to, again, transform this down into TensorFlow graphs. And so you can think of it as saying, hey, I have an if statement. I'm going to create an if node in the graph, like you say tf-cond. You have a multiply. Well, I'll turn that into a multiply node in the graph, and it becomes this tree transformation.
So where does the Swift for TensorFlow come in? Which is, parallels. For one, Swift is an interface, like Python is an interface to TensorFlow, but it seems like there's a lot more going on than just a different language interface. Yeah. There's optimization methodology.
Yeah. So the TensorFlow world has a couple of different, what I'd call front-end technologies. And so Swift and Python and Go and Rust and Julia and all these things share the TensorFlow graphs and all the runtime and everything that's later. Okay. Mm-hmm. And so Swift for TensorFlow is merely another front end for TensorFlow, just like any of these other systems are. There's a major difference between, I would say, three camps of technologies here. There's Python, which is a special case because the vast majority of the community efforts go into the Python interface. Mm-hmm. And Python has its own approaches for automatic differentiation. It has its own APIs and all this kind of stuff. There's Swift, which I'll talk about in a second. And then there's kind of everything else. And so the everything else are effectively language bindings. So they call into the TensorFlow runtime, but they usually don't have automatic differentiation, or they usually don't provide anything other than APIs that call the C APIs in TensorFlow. And so they're kind of wrappers for that. Swift is really kind of special, and it's a very different approach. Swift for TensorFlow, that is a very different approach, because there we're saying, let's look at all the problems that need to be solved in the full stack of the TensorFlow compilation process, if you think about it that way. Because TensorFlow is fundamentally a compiler. It takes models and then it makes them go fast on hardware. That's what a compiler does. And it has a front end, it has an optimizer, and it has many backends. And so if you think about it the right way, or if you look at it in a particular way, like, it is a compiler. Okay. And so Swift is merely another front end, but it's saying, in the design principle is saying, let's look at all the problems that we face as machine learning practitioners and what is the best possible way we can do that, given the fact that we can change literally anything in this entire stack. And Python, for example, where the vast majority of the engineering and effort has gone into, is constrained by being the best possible thing you can do with a Python library. Like, there are no Python language features that are added because of machine learning that I'm aware of. Right. They added a matrix multiplication operator with at, but that's as close as you get. And so with Swift, it's hard, but you can add language features to the language, and there's a community process for that. And so we look at these things and say, well, what is the right division of labor between the human programmer and the compiler? And Swift has a number of things that shift that balance. So because it's because it has a type system, for example, it makes certain things possible for analysis of the code, and the compiler can automatically build graphs for you without you thinking about them. Like, that's a big deal for a programmer. You just get free performance, you get clustering and fusion and optimization, things like that, without you as a programmer having to manually do it, because the compiler can do it for you. Automatic differentiation is another big deal, and it's, I think, one of the key contributions of the Swift for TensorFlow project is that there's this entire body of work on automatic differentiation that dates back to the Fortran days. People doing a tremendous amount of numerical computing in Fortran used to write these, what they call source-to-source translators, where you take a bunch of code, shove it into a mini compiler, and it would push out more Fortran code, but it would generate the backwards passes for your functions for you, the derivatives, right? And so in that work in the 70s, a tremendous number of optimizations, a tremendous number of techniques for fixing numerical instability and other kinds of problems were developed, but they're very difficult to port into a world where in eager execution you get an op by op at a time. Like, you need to be able to look at an entire function and be able to reason about what's going on. And so when you have a language integrated automatic differentiation, which is one of the things that the Swift project is focusing on, you can open all these techniques and reuse them in familiar ways. But the language integration piece has a bunch of design room in it, and it's also complicated.
The other piece of the puzzle here that's kind of interesting is TPUs at Google.
Yes.
So, we're in a new world with deep learning.
Yes.
It's constantly changing. And I imagine, without disclosing anything, I imagine, you're still innovating on the TPU front too.
Indeed.
So how much sort of interplay is there between software and hardware in trying to figure out how to together move towards an optimized solution?
There's an incredible amount. So we're on our third generation of TPUs, which are now 100 petaflops in a very large liquid-cooled box, a virtual box with no cover. And as you might imagine, we're not out of ideas yet. The great thing about TPUs is that they're a perfect example of hardware-software co-design. And so it's about saying, what hardware do we build to solve certain classes of machine learning problems? Well, the algorithms are changing. Like, the hardware takes, some cases years to produce, right? And so you have to make bets and decide what is going to happen. And so, and what is the best way to spend the transistors to get the maximum, performance per watt or area per cost, or like whatever it is that you're optimizing for. And so one of the amazing things about TPUs is this numeric format called bfloat16. bfloat16 is a compressed 16-bit floating point format, but it puts the bits in different places. In numeric terms, it has a smaller mantissa and a larger exponent. That means that it's less precise, but it can represent larger ranges of values, which in the machine learning context is really important and useful because sometimes you have very small gradients you want to accumulate and very, very small numbers that are important to move things as you're learning, but sometimes you have very large magnitude numbers as well. And bfloat 16 is not as precise. The mantissa is small, but it turns out the machine learning algorithms actually want to generalize. And so there's, theories that this actually increases the ability for the network to generalize across data sets. And regardless of whether it's good or bad, it's much cheaper at the hardware level to implement because the area and time of a multiplier is n squared in the number of bits in the mantissa, but it's linear with size of the exponent.
And you're connected to both
big deal.
efforts here, both on the hardware and the software side?
Yeah, and so that was a breakthrough coming from the research side and people working on optimizing network transport of weights across a network originally and trying to find ways to compress that. But then it got burned into silicon, and it's a key part of what makes TPU performance so amazing and great. Now, TPUs have many different aspects of it that are important, but the co-design between the low-level compiler bits and the software bits and the algorithms is all super important, and it's this amazing trifecta that only Google can do.
Yeah, that's super exciting. So can you tell me about MLIR project, previously the secretive one?
Yeah, so MLIR is a project that we announced at a compiler conference 3 weeks ago or something, at the Compilers for Machine Learning conference. Basically, if you look at TensorFlow as a compiler stack, it has a number of compiler algorithms within it. It also has a number of compilers that get embedded into it, and they're made by different vendors. For example, Google has XLA, which is a great compiler system. NVIDIA has TensorRT. Intel has ngraph. There's a number of these different compiler systems, and they're very hardware specific, and they're trying to solve different parts of the problems. But they're all kind of similar in a sense of they want to integrate with TensorFlow. Now, TensorFlow has an optimizer, and it has these different code generation technologies built in. The idea of MLIR is to build a common infrastructure to support all these different subsystems. And initially, it's to be able to make it so that they all plug in together and they can share a lot more code and can be reusable. But over time, we hope that the industry will start collaborating and sharing code, and instead of reinventing the same things over and over again, that we can actually foster some of that working together to solve common problem energy that has been useful in the compiler field before. Beyond that, MLIR is, some people have joked that it's kind of LLVM 2. It learns a lot about what LLVM has been good and what LLVM has done wrong, and it's a chance to fix that. And also there are challenges in the LLVM ecosystem as well, where LLVM is very good at the thing it was designed to do, but 20 years later, the world has changed and people are trying to solve higher level problems, and we need some new technology.
And what's the future of open source in this context?
Very soon. So it is not yet open source, but it will be hopefully.
So you
in the next
still
couple
believe
months.
in the value of open source in these kinds of
Oh yeah,
contexts?
absolutely. And I think that the TensorFlow community at large fully believes in open source.
So I mean, that's there is a difference between Apple, where you were previously, and Google now,
Yeah.
in spirit and culture. And I would say the open sourcing of TensorFlow was a seminal moment in the history of software, because here's this large company releasing a very large code base that's open sourcing. What are your thoughts on that? How happy or not were you to see that kind of degree of open sourcing?
So between the two, I prefer the Google approach, if that's what you're saying. The Apple approach makes sense given the historical context that Apple came from, but that's been 35 years ago. And I think that Apple is definitely adapting. And the way I look at it is that there's different kinds of concerns in the space, right? It is very rational for a business to care about making money. Like that fundamentally is what a business is about, right? But I think it's also incredibly realistic to say it's not your string library that's the thing that's going to make you money. It's going to be the amazing UI, product differentiating features, and other things like that you build on top of your string library. And so keeping your string library proprietary and secret and things like that is maybe not the important thing anymore, right? Where before, platforms were different, right? And even 15 years ago, things were a little bit different, but the world is changing. So Google strikes a very good balance, I think. And I think that TensorFlow being open source really changed the entire machine learning field, and it caused a revolution in its own right. And so I think it's amazingly forward looking, because I could have imagined, and I wasn't at Google at the time, but I could imagine a different context in a different world where a company says machine learning is critical to what we're doing. We're not going to give it to other people, right? And so that decision is a profoundly brilliant insight that I think has really led to the world being better, and better for Google as well.
And has all kinds of ripple effects. I think it is really, I mean, you can't understate Google deciding that, how profound that is for software. It's awesome.
Well, and it's been, and again, I can understand the concern about, if we release our machine learning software, our competitors could go faster. But on the other hand, I think that open sourcing TensorFlow has been fantastic for Google. Yeah. And I'm sure that decision was very non-obvious at the time, but I think it's worked out very well.
So let's try this real quick.
Yeah.
You were at Tesla for 5 months as the VP of Autopilot Software. You led the team during the transition from Hardware 1 to Hardware 2. I have a couple questions. So one, first of all, to me, that's one of the bravest engineering decisions undertaken really ever in the automotive industry, to me, software-wise, starting from scratch. It's a really brave engineering decision. So my one question is, what was that like? What was the challenge of that?
Do you mean the career decision of jumping from a comfortable, good job into the unknown, or
that combined? So at the individual level, you making that decision, and then when you show up, it's a really hard engineering problem.
Yes.
So you could just stay, maybe slow down, say Hardware 1, or those kinds of decisions. So just taking it full on. Let's do this from scratch. What was that like?
Well, so, I mean, I don't think Tesla has a culture of taking things slow and seeing how it goes. So, I mean, one of the things that attracted me about Tesla is it's very much a gung-ho, let's change the world, let's figure it out kind of a place. And so I have a huge amount of respect for that. Tesla has done very smart things with Hardware 1 in particular, and the Hardware 1 design was originally designed to be very simple automation features in the car for like traffic aware cruise control and things like that. And the fact that they were able to effectively feature creep it into lane holding and a very useful driver assistance feature is pretty astounding, particularly given the details of the hardware. Hardware 2 built on that in a lot of ways. And the challenge there was that they were transitioning from a third-party provided vision stack to an in-house built vision stack. And so for the first step, which I mostly helped with, was getting onto that new vision stack. And that was very challenging. And it was time critical for various reasons, and it was a big leap, but it was fortunate that it built on a lot of the knowledge and expertise and the team that had built Hardware 1's driver assistance features.
So you spoke in a collected and kind way about your time at Tesla, but it was ultimately not a good fit. Elon Musk, we've talked on this podcast, several guests of the course. Elon Musk continues to do some of the most bold and innovative engineering work in the world, at times at the cost to some of the members of the Tesla team. What did you learn about this working in this chaotic world with Elon?
Yeah, so I guess I would say that when I was at Tesla, I experienced and saw the highest degree of turnover I'd ever seen in a company,
right,
which was a bit of a shock. But one of the things I learned and I came to respect is that Elon's able to attract amazing talent because he has a very clear vision of the future, and he can get people to buy into it because they want that future to happen, right? And the power of vision is something that I have a tremendous amount of respect for. And I think that Elon is fairly singular in the world in terms of the things he's able to get people to believe in. And there may be people that stand on the street corner and say, we're going to go to Mars, right? Yeah. But then there are a few people that can get others to buy into it and believe it and build the path and make it happen. And so I respect that. I don't respect all of his methods, but I have a huge amount of respect for that.
You've mentioned in a few places, including in this context, working hard. What does it mean to work hard? And when you look back at your life, what were some of the most brutal periods of having to really sort of put everything you have into something?
Yeah, good question. So working hard can be defined a lot of different ways. So a lot of hours, and so that is true. The thing to me that's the hardest is both being short-term focused on delivering and executing and making a thing happen, while also thinking about the longer term and trying to balance that, right? Because if you are myopically focused on solving a task and getting that done, and only think about that incremental next step, you will miss the next big hill you should jump over to, right? And so I've been really fortunate that I've been able to kind of oscillate between the two. And historically at Apple, for example, that was made possible because I was able to work with some really amazing people and build up teams and leadership structures and allow them to grow in their careers and take on responsibility, thereby freeing up me to be a little bit crazy and thinking about the next thing. And so it's a lot of that, but it's also about, with experience, you make connections that other people don't necessarily make. And so I think that's a big part as well. But the bedrock is just a lot of hours, and that's okay with me. There's different theories on work-life balance, and my theory for myself, which I do not project onto the team, but my theory for myself is that, I want to love what I'm doing and work really hard. And my purpose, I feel like, and my goal is to change the world and make it a better place. And that's what I'm really motivated to do.
So last question, LLVM logo is a dragon.
Yeah.
You explain that this is because dragons have connotations of power, speed, intelligence. It can also be sleek, elegant, and modular, though you remove the modular part. What is your favorite dragon-related character from fiction, video, or movies?
So those are all very kind ways of explaining it. Do you want to know the real reason it's a dragon?
Well, yeah.
Is that better? So there's a seminal book on compiler design called The Dragon Book. And so this is a really old now book on compilers. And so the dragon logo for LLVM came about because at Apple, we kept talking about LLVM related technologies and there's no logo to put on a slide. Right. Yeah. And so we're like, what do we do? And somebody's like, well, what kind of logo should a compiler technology have? And I'm like, I don't know. I mean, the dragon is the best thing that we've got. And, Apple somehow magically came up with the logo, and and it was a great thing, and the whole community rallied around it, and then it got better as other graphic designers got involved. But that's originally where it came from.
The story. Is there dragons from fiction that you connect with? For Game of Thrones, Lord of the Rings, that kind of thing?
Lord of the Rings is great. I also like role-playing games and things like computer role-playing games, and so dragons often show up in there. But really, it comes back to the book. Oh no, we need a thing.
Yeah.
And hilariously, one of the funny things about LLVM is that my wife, who's amazing, runs the LLVM Foundation. And she goes to Grace Hopper and is trying to get more women involved in she's also a compiler engineer, so she's trying to get other women to get interested in compilers and things like this. And so she hands out the stickers, and people like the LLVM sticker because of Game of Thrones. And so sometimes culture has this helpful effect to get the next generation of compiler engineers engaged with the cause.
Okay, awesome. Chris, thanks so much for talking.
It's been great talking with you.